We have Diego.
Yep.
Yeah. You can hear us. We can hear you.
And you should see my screen now.
Yeah. Perfect.
Okay. So
We don't have the full screen. 1 second.
now you should have it.
Yeah. Perfect. So our next talk will be given by Diego Turrini about Mercury-Arxes. Please go ahead.
Okay, so Mercury-Arxes is part of our suite of codes. Is actually the correct spelling is with a key, so it's the Mercury-Arxes, which stands for origin. So it takes the name from the fact that it builds on top of the Mercury embodied code, which is a long-time classic in the planet formation and dynamical studies community, but it integrates it with the VH-FAST library from the Rebound code, because we noticed that when we want to account for migration, sometimes the inbuilt libraries of Mercury are not necessarily precise. The Arxes part of the name comes instead from the library we developed that accounts for the growth, the migration, and the interaction between disk and gas of planetary body. So the code is a mix, as you can see from the old Fortran 77 for the body of Mercury, C99 for the VH-FAST library, and Fortran 2003 for our Arxes library. The code is parallel and vectorized, so we try to squeeze every drop of juice out of our servers, and we are working in a framework of the newly born Italian supercomputing center to port the code to GPU computing. There are also ongoing work to expand the code with new dynamical and physical library. I will mention which ones in a bit, but then I will talk about it later on today. And there are also a suite of satellites code, which together with Jade that Elenia already presented, form what our Arxes suite of code for planet formation studies. So what does Mercury-Arxes does? Well, it contains a library for multi-phase growth track that account for a first phase with core formation and envelope capture, and a second phase with runaway gas accretion using a parametric approach. So basically, we tell the planet, you need we tell the simulation, you need to form this planet over this time, and then start the runaway reach to this final mass. The growth curve, however, are compatible with both the pebble accretion and the planetesimal accretion curves. So you can try to mimic the behavior of other or the physical scenario that you prefer. There is a multi-phase migration treatment with a linear migration regime adapted using the treatment from Kevin Walsh 2011 paper, and a power law migration regime from Anne Malhotra 2005, and they allow to basically reproduce the migration tracks from the Bern code, the first version of the Bern code from Ordazini et al. 2015. Then we have another important element, which is the radius evolution of the planet. So we have we account for the phase of expanded atmosphere, where the radius of the planet is dominated by this very rarefied but huge envelope, and then the envelope contraction during the runaway gas accretion. And finally, there is the gas planetesimal interaction module, which has the classic damping effect of gas drag, but using an improved treatment for the coupling coefficient of gas and dust, gas and solids, instead of the classical one for Wedge shielding, which however has been shown not to be continuous and therefore not necessarily correct in all regimes. And then we have the treatment of the excitation caused by the disk gravity, which has been calibrated with hydrodynamical simulation. The physical library is going to be, and the dynamical libraries are going to be expanded with new treatment that account for more realistic migration and growth tracks based on the pebble accretion scenario. So when we run a simulation, the end results we get are summarized in this animation. So we have the dynamical state of the system, which the code takes snapshot over time. So we can have we can study the system at different slicing of time, or just uncompress the evolution of single bodies, like with the classic Mercury. On the top right, you can see that we track both the mass growth, the orange curve of the planet, and the radius growth. Both curves are normalized to the final value, so they finish at 1. but you see that during the core growth, the planet is characterized by a huge radius, which influence its accretion efficiency. In the bottom right plot, you see the orange curve in linear scale instead of logarithmic, and is together with the migration track. So you see the semi-major axis this time normalized to the initial radius. So we end up with a fraction of AU. This simulation started 19 astronomical units and the planet ends up at 0.5 AU. And the blue curve is the planetesimal flux impacting on the planet during the growth and migration, accounting for its physical radius as capture radius. We track the source region with Mercury-Arxes of all the impacting planetesimal, and in the bottom left you see the evolution over time of the partition of the accreted particle from the different regions of the disk. Here in this simulation, we divided the disk in different compositional region, but in principle, you can track the whole continuum of formation regions. And this is a multi-planet simulation with our migration, the inclusion of gas drag and excitation allow us to treat in a realistic way the dynamical transport and implantation of planetary bodies. For example, these are 100-kilometer large planetesimal that, contrary to popular belief, they are influenced by gas drag when they enter the inner regions of the disk if they have very high eccentricity and therefore very high relative velocity with the gas. And you see that there is this fountain because it is implanting the planetesimals. And we also expanded the code with an updated ejection criterion. The classical Mercury just let you input an ejection distance, which could be for convenience to make the simulation light. But instead, we only eject the planetesimal bodies that become unbound, so on hyperbolic or parabolic orbits, in order to study the mass loss by the system in a realistic way. As I mentioned, Mercury-Arxes is part of a suite of code. One of the code that we implement that integrate Mercury-Arxes is Hephaestus, which is actually a post-processing pipeline that combines the output of Mercury-Arxes in terms of flux of impactors and gas accretion, combine it with the JADE output, gives the composition of the disk over time, and basically it gives us the evolution of the composition of the planet element-wise, so element by element of a spectrum of 20 elements, until it gives us the final composition. And we are using this basically to trace the competing effect of gas and solid accretion onto planet to determine the composition. Another code that I will tell you more later on today is Gromit, which is actually a pebble accretion code that accounts also for migration. And we're using this basically to calibrate the growth and migration tracks of Mercury-Arxes. So yes, they are parametric, but we link them to the disk environment and the condition of the pebble transport we want to consider in order to have realistic migration and growth tracks instead of just arbitrary one. And finally, we have the BRI code. The BRI is a parallel statistical collisional code. Why statistical? Because it works in tandem with FARI, which is a collisional probability code that uses algorithms that have been used for more than a lot, 50 years in the solar system community. So basically it takes the output of Mercury-Arxes at the time you want to analyze, consider the eccentricities of the bodies and the semi-major axis, compute the probability of intersecting orbits, and then output collisional probabilities and impact velocity. For example, the distribution of the impact velocities at each position is plotted here. The lighter the color, the higher the impact velocity. And these data are passed to the BRI that rates the bodies, attributes to them a mass in terms of a swarm mass, and then depending on the size frequency distribution we want to use, and using updated scaling law for collisional evolution, it tells us how much mass is lost during the impact and how much it goes into dust. Why the dust is interesting, especially in the context of this cost action, because we generally think of the dust we see in disk as primordial dust, the dust from which the planet formation process starts. However, we know from the solar system and debris disk that collision produce dust. So debris disk are the effect of this collision over a circular time scale, but in reality, collision and dust production start the very moment we have planetary bodies in the protoplanetary disk, like planetesimal, and we have at least one massive perturber that excites the velocity. And what we obtain when we process, for example, the radial distribution of dust with debris are this kind of curve. The two columns on the left are for G-type star, so solar type star. The two columns on the right are for M stars. You see the curves are similar, independent on the stellar mass. What are there? On the bottom, on the top line, you have the dust production per AU ring. So the total dust collisionally produced per AU, 1 AU wide ring. And you see there are peaks and valleys. These are basically structures of rings and gaps created by the presence of the planets and the collisional production of dust, exactly like the ones we see in disk, making things even worse because we don't know if these rings are the starting point or the end result. The gray curves are for planets that are forming in situ, but the colored one are for planets that are migrating. And as you can see, there are still the peaks, even if the distribution changes. And migration is with only one planet, so one planet can create multiple peaks when it is migrating. Below you see instead the temporal evolution, for example, because we can resolve that also the dimension over time, combining debris and Mercury-Arxes, and you see that there can be multiple peaks. For example, one when the core reaches its final peak mass, and then another one when there is the runaway gas accretion. So this is a very brief introduction to all the set of things we can do with Mercury-Arxes and the satellite code of the Arxes suite. Thank you for your attention.
Thank you very much. The talk is open for questions. Yeah, go ahead, Maria.
Yes, Diego, thank you for this nice talk. I am wondering about the targets that we can use to compare or apply with your model. We can apply this model with the classical protoplanetary jaundice, or there is this in around very old stars. So far as I know, there are no detection of debris around, for instance, for stars with a age as our sun. No, we can comment how for the targets required to compare with these kinds of models, or there are used for the case of protoplanetary disk or for stars as our solar systems.
So at the moment, the principal case study we did was on HD 163296, which is a disk around an A-type star, and is one of the best studied disks. And we actually do have indication that this disk could host this collisionally produced dust, mostly because if you have a giant planet forming, like this system, it hosts 4 planets. You can see it in this simulation. There are 3. There is 4th planet discovered after our work outside the ring, the protoplanetary disk we are considering. So these giant planets should act as a barrier to the migration of dust. So you would expect that the region inside the innermost giant planet should be devoided by dust, because the dust or the pebbles drift inward, and therefore and they are not replenished because of the barrier. However, that very region is the region where we have the peak of the dust abundance in the disk. And this is explained both qualitatively and quantitatively by planetesimal collision, because it is the region also of the peak velocity, because the pericenter are here. There are other possible indications in the distribution of dust over time in disk. I didn't put this because I was focusing on the code rather than and the capabilities rather than the results. But if you look at there is a paper by Leonardo Testi in 2022 where they study star forming region at different time around different kind of stars. So also for solar type star. So disk that could in principle be compatible with the solar nebula. And I see that there is a decrease, the expected decrease in the total dust abundance over time until 1 or 2 million years. But a 2 million year disk on average seems to show a resurgence of dust. And this can be explained, it's actually what we studied in the Bernard-Baugh 2022 paper, also with Leonardo, by the production of dust. So if planets, giant planets, form on a timescale of 1 to 2 million years, which is in agreement with also the pebble accretion scenario, that's the time where you have the most efficient giant planet accretion. And we know the planetesimal can appear in the first 1 million years, because in the solar system we have meteoritic data that say so. Then the moment you mix the two, you end up getting collisional production. So disks that are efficient in producing planetesimals should also produce this kind of dust.
Okay. You mentioned that the targets are very old, no? No, young stars. These debris are around young stars.
These are protoplanetary disks, not debris disk.
Okay.
So we are talking about things that are 1 to 5 million years old.
Okay, thank you.
Okay, so I have another question. Maybe you said it and I missed it. So this code is available on collaborative basis, or?
Yes, I didn't say it. So all these codes are available on collaborative basis. So we're open to collaboration. There are plans to release part of this code as public. Over time, we plan to release the whole suite as public, like it has been done, for example, for the ExoClimb suite. It's just that at the moment they are not user-friendly yet, and we are still tweaking with them in order to improve the physics and finalize everything. So they are usable, and they will become available sometime in the future, but at the moment they are already available through collaborations.
Thank you. Then the other question is, could you say something about the runtime? Like, I guess it's similar to the normal Mercury standard code, or did
well, this one is parallel. So depending on the number of core you use, Mercury-Arxes is faster. We found that the sweet spot is using a limited number of core for up to 100,000 particles in the simulation. So like using 8 cores, you tend to get a speed up of a factor of 4 or 5 with respect to the typical simulation, because about 90% of the workload of Mercury is parallelized for this kind of simulation. And you can run multiple simulation over the same server, so you get a better speed up than increasing. But if you want to run larger simulation, you can just increase the number of core that you use. With 8 cores and 100,000 particles, we run a simulation in roughly 10 days.
Oh, that's very good. Very cool. Are there any other questions? This does not seem to be the case. So thank you very much, Diego. It's very cool stuff.
Thanks to you.
Thank you.